This is Max Halperin. I'm going to demonstrate how I would develop in Java a dynamic programming approach to solving the longest common subsequence, or LCS, problem. This is analogous to the global sequence alignment problem for which you have a project. I'm going to concentrate on how to develop very systematic, straightforward code where the dynamic programming approach is derived from a simpler recursive approach. My focus is on getting the right answer, getting correct code, and the result is it's not quite as fine-tuned for efficiency as the version that Sedgwick and Wayne show. It's just a little bit different, but honestly, the fine-tuning they do has very little impact. The additional efficiency is very minor compared with the difference between the original recursive version and any sort of a dynamic programming approach. And in any case, if you do want to do the fine-tuning, the right time to do that would be at the end after you've got straightforward code working. I'd be happy at that point to show you how you can do that and get code that's essentially the same as Sedgwick's. In any case, I've created this LCS project. I've put the standard library in and added it to the build path so that those facilities are available. I've made an LCS class in the default package with a stub main. These are all things you're used to, and that means we're ready to get actually to work on the code. So in the main method here, what I want to put in is some code that's going to calculate initially just how long of a common subsequence two strings have, but we're also going to time how long that takes so that we can compare the recursive and dynamic programming version. So to do the timing, I'll use a library class called stopwatch, and if I make a new stopwatch object, that's keeping track of the time since when it's created. It keeps track in seconds down to the nearest millisecond. So with that going, the stopwatch is running, I can find the length that I get if I recursively calculate the LCS length for two example strings. Let's find how much in common spanking and amputation have. It's underlined because we haven't written the recursive LCS length method yet. That's still left to go. And then we can find the time it took by taking our stopwatch and finding the elapsed time. And then we're ready to print out our answer. So our recursive LCS length is some decimal integer, and the time it took to find it, I'll use a decimal point with 3 places after it in a floating precision floating point number, because the time, as I said, it's in seconds, but just down to the milliseconds. That's 3 decimal places. So with that code in place, we need to then think about, okay, how am I going to actually write this? I can use this quick fix if I hover over it and actually create the method that way. Instead of saying string and string2, let's call the parameters x and y for consistency with your notes from the Sedgwick textbook. And I'm going to also put a comment on here. If I go to the source menu, generate element comment, that just keeps track of what this procedure does, because we're going to have a bunch of different methods. So this computes the length of a longest common subsequence, or LCS, of x and y, and takes the parameters x and y and it returns the LCS length. And right now it's always returning 0 because we haven't written anything in there, it's just the stub. But already I could save this out and try running it just to make sure I've got my basic testing framework right. Sure enough, length of 0 in no time at all seems to be printing out right. So now I can actually go in here and start putting in some recursive code. And the basic idea here is that we're going to be looking at shorter suffixes of x and y, like all but the first character of x or all but the first character of y. And rather than literally taking the substrings, which is pretty clumsy to do in Java, we're going to take an alternate approach of just keeping track of how many characters in x and y we've skipped over. And if we've gone past 3 characters in x, what's left is the suffix starting at position 3 in x. We can just leave the whole string intact and just keep track of the positions. So what I'm going to do here is I'm going to call a helper procedure. I can call that helper procedure by the same name, recursive LCS length. It's just a more general version that takes not just x and y, but also a position to start at x and a position to start at in y. So this is 0 and 0. That's after 0 characters of x are already passed, after 0 characters in y are already passed. So I'll just make a little comment. Suffixes starting at positions 0 and 0 are the whole strings. Just to mind why this makes sense. And again, we can create this method using the quick fix. X, Y, I, and J. I could again create a comment on there, edit the, or go into the source menu rather and generate an element comment. And this one also returns the LCS length. As far as the description of what it does, we could actually copy and paste from here to get most of it. Copy, go down here, paste. It computes the length of a longest common subsequence of suffixes of x and y, starting at positions I and j. And so now we're finally serious about doing this recursively. No more passing the buck to a helper method, which means we need to start with an if that checks for a base case. Is something so small, so simple, we can't make it smaller. So the case where we can't make x smaller by taking a suffix of it is if I is already equal to the length of x. And in that case, since there's nothing left in the x string, once we've reached the end of it, the number of characters left in common with y has got to be 0. And there's another symmetrical base case. If j is equal to y's length, then likewise the base case value is 0. And not every dynamic programming problem or all the base case values going to be the same or all be 0. But for this problem, it makes sense. If there's no string, there's no common subsequence. And finally, we're left with the general case where neither I nor j has reached the end yet, where we could make some progress. Towards our base case. And we would do that by shortening at least one of the suffixes. So we're either going to advance I further towards the end, or advance j, or maybe both. So there are several options to consider here. The first option would be if we shorten the suffix of x by advancing the I position. So we could compute with a recursive call. This is the recursive version. What we get if we look at x and y, but starting at not position I, but position I plus 1 and j. So that's going to have less of the X string available. The other option we could consider symmetrically would be to look at X and Y starting at I, but at position J plus 1 in the Y string. And there's still a third option, so let me maybe keep track of what we're doing with some comments. This is if we skip over X sub I, and this is if we skip over Y sub J. Option 3 would be, what if we move past both of those characters? So we have I plus 1 and J plus 1, which I guess would be skipping both. But there's actually something interesting. If you're going to find the longest common subsequence you can form without using the first character of X and without using the first character of Y, well, there's a possibility maybe those two first characters are the same, in which case you could add that as one character of your longest common subsequence. Get a longer subsequence starting at I and J than you do starting at I plus 1 and J plus 1. Maybe we don't actually skip over those two characters, maybe we use them. And that would happen if, if X's character at position I is the same as Y's character at position J, then in that case we can take option 3 and we can increase it by one character because we've found one character in common. And remember, we're trying to find as many characters in common as we can. So we've got these three options, and the thing to keep in mind is the particular kind of optimization we're doing is we're looking for the longest common subsequence. So that's going to be the maximum of the options. Some optimization problems, you're trying to make something as small as you can, like a cost, but here we're looking for as big as you can. So the value we're going to actually return is the biggest of options 1, 2, and 3. Math.max can find the biggest of two numbers. We can just use it twice. Take the biggest of option 1 and another math.max of option 2 and option 3. That would give us the biggest of all three. And at this point, I've got a hopefully working recursive LCS length. There's really no way to know without trying it. So I'll save it out. We'll click the Run button. And it says there are 4 characters in common. And if you've seen this particular example of spanking and amputation before, you know that that's right. There is a 4-character word they have in common. It also is taking a little longer now, not immeasurably small time, not less than a millisecond. This is now 4/100ths of a second, 40 milliseconds, which still is very fast. You didn't really notice the computation happening. For a human, 4/100ths of a second is a brief period. But for a computer that can do billions of computations a second, 4/100ths of a second, that would mean that it must be doing tens of millions of operations just for these 2 short words. It's not actually a very efficient approach. There's a lot of redundancy, and we'll see that what's really the issue is that as the strings get longer, the time grows very rapidly. If we tried longer strings, it would, even for us humans, seem like way too long. So that's why we're going to do the dynamic programming version, at which point I can actually try that experiment with longer strings, and you can see how different the two are in terms of the scaling up. This would be actually a good time to stop and do more tests with other strings, make sure we're confident that this version is correct. I'm not going to take the time now to do that, but you ought to. And the reason this is a good time to do it is because once we've got a working, correct recursive version, it's going to be very mechanical to translate it into the dynamic programming version, which ought to work just as well, except a lot faster. So let's do that. The dynamic programming version we can do by initially taking this recursive version that we've got here and just making a copy of that and pasting that in. So I'll go here to the end, and I'm just going to change the name of this to the dynamic programming DP LCS length. And at the moment, it just is the same. It's the recursive version, so that's a lie to call it the dynamic programming version. But what we're going to do is we're going to make a table with all the values for the different values of I and j, the different starting points for the suffixes. And so the idea is that we're going to have this optimizing table, I'll call it opt, where if we look at position ij in the table, it contains the same value as we would get if we were to use our recursive version with I and j. And so that table is, let's say that we can declare that to be a two-dimensional integer array, and how big it needs to be. Well, it needs to be big enough for all the possible values of I and all the possible values of j. I can be as small as 0 or as big as the length of x, so we need to have room all the way up to the length of x, which means one more value starting at 0 going up to the length of x. And similarly, we can use one more than the length of y. And here's the point. Once we get this table filled in, so I'll make a reminder note here, fill in the table, then we never have to call this procedure. If we want to know what this procedure would produce with I being 0 and j being 0, we can just look in the table and find the value that's there. That's the whole point. We still have to fill in the table, but basically we've got the outline. And at the moment, since the table starts out with all zeros in it in Java, it's going to be returning 0. We could try it out and make sure it's working in the sense that it does return 0 and is fast, get basically our testing framework in place. So I could just take these same 4 lines, cut those and paste twice, so we have 2 copies, and instead of calling the recursive LCS length, we'll call the DP LCS length, and clarify that that's what we're printing out. Can't use these same names again, so we just rename the second copy of the variables. And probably rather than having 2 copies of spanking and amputation, to make it clear that we really want to run the same test twice, I should factor those out. So if I select that and I go to refactor, extract local variable, Command Option L is the shortcut for that. You can call that X, and similarly here for amputation, Command Option L, call that Y. You see I've got replace all occurrences checked. And so that's why it's not just X and Y here, it's X and Y there, and that's what's making it evident that we're doing the same test both times. Probably a little cleaner if I wait till after those declarations to start my stopwatch going. So if I run this, you can see the dynamic programming version is much faster, less than a millisecond. Instead of, this time it was 18 milliseconds. So, there's some variability. Often the first time you run a program, it's slower. But the value's not right. It's saying 0 instead of 4. And our goal is going to be to get it to have the right value and still be essentially just as fast, or pretty close anyway. And that's what we've still got ahead of us. By the way, I purposely put the dynamic programming version ahead of the recursive version in the testing, so that if we ever try it with some long strings and the recursive version is taking forever and we get fed up and hit the red stop button, we'll already have the dynamic programming answer out. So anyway, let's go and do this filling in the table part. So it's a two-dimensional table. We need to fill it in for all possible values of I combined with all possible values of j. So that sounds like a two-dimensional loop for int I equals something, 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 some loop over the different I values. And then within that, loop over all the possible j values. And in the middle here, this is where we're going to fill in position ij in the table. And rather than getting the loop stuff filled in first, the something, 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 I'm going to put that off, and I would urge you to do that too, because I find it easier to get those loop control elements right once I see what the loop body is going to be. And where I'm going to get the loop body from is I'm going to go to my recursive version, and I'm going to copy all that code from the recursive method, and I'm going to take it here into this middle of these two loops and paste it in there. And that's not quite right yet, but it's a really good starting point. So one problem it's got is it's not doing the right thing. It's supposed to be filling in this opt ij, and instead it's returning. So that's easy to fix. You can just put that in. And I'm going to copy this opt ij equals part. And everywhere in this code that I copied in, where there's a return, I'm just going to paste over the top of that opt ij equals. So it's now in the business of filling in the table rather than returning a value. The returning happens here at the end when we get the value from position 0, 0. And of course we're doing that because that's should, when we're to that point, have the value that the recursive method would give, with I being 0 and j being 0. And we can do that same thing for these three recursive calls. So the general pattern is, instead of returning value, we store into the table, and symmetrically, instead of calling the procedure, that's when we fetch from the table. So here I'm going to fetch from I plus 1 and j, and here I'm going to fetch from I and j plus 1, and here is the case where we're looking at I plus 1 and j plus 1. So, three places I used to return, I'm now storing there, and there, and there. And the three places I was making recursive calls, I'm now retrieving. as well as the one starting call is a retrieval. So we save it out. We're not done yet. I just like saving every once in a while. And we have to think about these loops. And the thing is, with these recursive calls now visible as table lookups, we recognize we need to have already filled in position I plus 1. We need to have already filled in position j plus 1 when we're working on position ij. Otherwise, we wouldn't have the right value to fetch from there. So that says we need to work from bigger values down to small values. We need to start with I as big as it can possibly be and decrease I from there until, well, as long as it's still greater than or equal to 0. Oops, not I, not x rather, but I, as long as that's greater than or equal to 0. And similarly here, so long as y is, well, so long as j is greater than or equal to 0, we're going to reduce j. So we can sort of double check by looking at our base cases. The very first thing the loop does is when I and j are their lengths. And that's really good because at the beginning of the loop, nothing's been filled into the table yet. We wouldn't be able to do these lookups successfully yet. We must be starting out as the very first thing we do in these base cases. And sure enough, I and j start right where those base cases are. So that's a good sign. So if I save again and run, you can see we got our desired result, that the answer from the dynamic programming and the recursive version are both 4, but the dynamic programming version is still taking an immeasurably short time, less than a millisecond, whereas the recursive one is at least in the tens of milliseconds. For this short of a computation, there's a lot of variability. If we look at longer ones, we probably won't see it bobbing around quite so much. But you can see already there's this huge difference. So I guess we might as well try scaling up to something bigger. I don't have anything quite so clever, but if you know what's going to happen, you know that spanking and amputation have pain in common. So we've got spanking hurts and amputation too. And if we run that, now there are 5 characters in common. Still didn't take the dynamic programming version even a millisecond to compute. The recursive one is still running. Oh, there it is, over 10 seconds to find that answer. So just a few more characters on the end, and it went up from tens of milliseconds to 10 seconds. It's just scaling up horribly as the strings get longer. At any rate, our next goal is, rather than just finding that these words have 4 or 5 characters in common, to find out what those characters are. So we'll make a new procedure that's going to actually use the dynamic programming approach, but instead of just finding the length, it's going to find an actual longest common subsequence. And it's going to have a lot in common with this. All this optimizing table stuff is going to be the same. It's just going to make different use of that optimizing table. So it'd be nice if we could factor all this code out so that it can be shared between the two versions. We can do that in our refactor menu, extract a method. Takes x and y. We can call it something like the optimizing table method. It makes the optimizing table. And so now this is suddenly a much shorter, simpler method because it's calling the helper to do all the work of building the table. And then it just says, okay, then once we've got the table built, go to position 0, 0. And here's the code we wrote for how to fill in the table. That's been factored out into this separate optimizing table method now. Give that a comment saying that it produces a table of the LCS lengths for all suffixes of x and y, and it returns a table with position I, j being for suffixes starting at I and j. So once we've got that table, then we can look at taking this method for finding the length and doing something similar for finding the sequence itself. And again, it may make sense to go into our main method and put some testing code. We can say that we can find the LCS using a method that we're going to write and pass into that x and y and print it out as a string. So that's our testing code, but it's telling us we have to write this. So that's fine, we'll write that. And let's see, we might as well put our element comment on there. So this returns a longest, just say an LCS of x and y. I'm being careful here. I'm saying that this computes a longest common subsequence rather than the longest common subsequence, because there can be a tie. There can be a couple that are equally long. And we're going to start out this with that same finding of the optimizing table. That we used in finding the length. And what we're going to do is we're basically going to kind of reconstruct how the choices were made, how it was that one of options 1, 2, and 3 was found to be the best option at each point, and use that to build up our string. And so we're supposed to return a string at the end. I'm talking about building one up. For that, I find there's a helpful library class that I use really in any procedure that's going to build up a string incrementally and then return it, and that's a string builder. And at the end, what we're going to return is the result of converting our string builder to a string. So what needs to go in the middle here is the stuff that actually appends all the appropriate characters to that string builder to be the longest common subsequence. So what we do is we're going to start out with I at the beginning and j at the beginning, and have a while loop that is going to keep going, putting more and more characters into the string builder as we find them to be in common, and advancing I or advancing j, or maybe advancing both of them. I find these loops easiest to write, easiest to get correct, if I just make it a while true, so an infinite loop, on the surface infinite. But what we're going to do is when we reach a base case and we discover we're all done, then at that point we can break out of the loop. So this code that's going to go in the middle here, it's going to be real similar to what we've got in the building of the dynamic programming table, where we've got a couple base cases and we've got some options to choose between, right? This is also the same code as what we had in the recursive version, essentially, right? They're all going to be pretty much the same, because they're all solving the same problem. So let's see, where were we? Here we are in our while loop. I'm going to paste that in. So if the goal, now we're not trying to store things into the table. We're actually going to be reading what's in the table and using it. If I is equal to x dot length, at that point, I guess I could maybe make a comment out of this. We know that opt ij is equal to 0. And there's nothing more. And that has to do with what our base case is, that there's nothing in common once you get to the end of either of the strings. Other dynamic programming problems, there might still be something to finish up at the end. But here, we're all done, so we can just break. And similarly, in this case, we know we're at an ending point, and so we can break out of the loop. And then we can look at our options. And we don't actually need option 3 because if neither option 1 nor option 2 is right, option 3 must be. So what we're going to do is we're going to look at which of those 3 options, 1, 2, 3, was in fact chosen as the largest. So we've got some ifs. We're going to say if the opt ij is equal to option 1, then what do we do? And otherwise, if it's equal to option 2, and so forth. So if it's equal to option 1, well, the comment up here tells us that's when you skip over xi. So we'll just increase I. And else if opt ij is equal to option 2, I can keep typing this wrong, but that's when we skip over y sub j. And see, this is where I know I'm in option 3, because I didn't have the right value for option 1 or option 2. And so this is where we're going to advance both I and j. But there was something more important to do, which is that this is where we might, in fact, probably do have a character in common. That if we find the character at position I of x, and that's the same as the character at position j of y, then we've located a common character. And so that's going to go into our string builder. We can just append the character. It doesn't matter whether I call it x's character or y, because we know that they're the same. I'll just put x's character in there. And that hopefully is what it takes, that every time we find a common character, that's option 3, so we're increasing both I and j. Notice I don't do that until after I've used I and j. So let's give this a whirl, see if it works. So the 5 characters in common between spanking hurts and amputation 2 is paint. Maybe that's a therapy if you're in pain for those reasons. Oh, it looks like I didn't put new line character. It's a little ugly, the recursive one starts right on the same line. Well, that's easy to fix. \n for the new line here. You can also just go back to the original version, spanking and amputation, which have 4 characters in common. Run it, and those 4 characters are pain. That's what spanking and amputation have in common. You can find it faster with dynamic programming. So that's how I would develop this code, and I recommend you do the same process for the global sequence alignment problem.